This video demonstrates the training of an artificial agent. As the picture indicates, the problem is about selecting between two paths. One of a path gives a coin in the end, a delayed reward. A unique feature of the video is that it will illustrate how the memory of an agent evolves using reinforcement learning. In the splitting path prediction problem, the policy is already given. The agent always moves east except in the center location. In this location, it randomly selects action north or south. The challenge is to estimate the value function, expressing how good it is to be in a state. The value is defined as the estimated sum of future rewards for a given policy. The state is defined by two variables, x and y, a two-dimensional position. The x position ranges from 0 to 4. The y position can take one of three values, 0, 1, and 2. The starting position is always at x equals 0 and y equal to 1. If the agent moves into the coin, it receives a positive reward of 1. All other locations gives 0 reward, for example, the end of the south lane.
One of the variants applied to fit the value is one-step temporal difference learning, as the relation expresses the value of state S depends on a single reward and the value of the next state. This is illustrated for the start state. Learning from only one step ahead has been applied in earlier videos, for example, the treasure problem. Monte Carlo prediction or learning is a candidate alternative for updating the value function. In this variant, as the relation expresses, all the rewards from an episode are used. Consequently, the function fitting can only be performed after the episode has ended. So the value of the start state depends on all rewards along the blue marked path. The updating variant presented here is a hybrid. It is somewhere between one-step and Monte Carlo prediction, as the relations indicate multiple rewards are used for value function updating. The blue arrows in the figure shows a possible scenario. The start state is updated from 3 rewards and the future states 3 states ahead. For many RL problems, n-step prediction is the most efficient alternative.
The frame on the left represents the environment. The black object denotes the agent position. This frame also displays information such as the number of elapsed episodes. The frame on the right shows the agent's memory, in this problem expressed solely by the value function. Here states close to the coin happens to have a good value. This time we predict the memory from a single step. Single-step updating was also used in the road and treasure problems, presented in preceding videos. Let us pause for a moment and reflect. Only one state is affected when the coin is found. And now let us fast forward until 50 episodes have been performed. Still, only a few state values have been changed. The explanation is that it takes time until the single reward at the end of the upper path spreads to preceding states. Consequently, learning becomes slow. Many more episodes are needed in the one-step setup for the value function to converge. A new agent training now begins. This time we use the Monte Carlo method. In this method, all rewards during an episode is used for memory updating. Let us pause for a moment and reflect. Now many more states are affected. This results in a more desirable fitting of the value function. Directly from the very first episode in which the coin was found, the value function of the start state was affected. And now let us fast forward until 50 episodes have been performed. When trained, the value function fits well with intuition. For example, do all states in the upper lane have the same value? A new agent training now begins. This time we use the n-step method. The horizon is set to 3. Let us pause for a moment and reflect. In contrast to the one-step method, several states are affected when the coin is found. And now let us fast forward until 50 episodes have been performed. Again using n-step prediction. Wonderful! The value function converged after only 50 episodes. The value of being in some of the cells to the left of the split is lower than in the cells in the upper lane. This is because there is a 50% chance of moving to the lower lane, where no coin is given, when starting from a cell to the left of the split. The problem presented here is one of many example problems described in the book Reinforcement Learning Explained. This was only a brief description. Many more details are presented in the book. Please visit the book's homepage for more information.